Dan Collins. Dan got his PhD from New York University. He's worked at Lawrence Livermore Labs, University of Cape Town, Georgia Tech, and he joined CPC in 2006. He's worked on statistical prediction methods, model post-processing, and climate predictability studies. And the title of his talk is Climate Change and the Predictability of Extreme Events. Dan?
Thank you. Okay. So I'm not going to focus too much on extreme events. I've been doing analysis of climate change and predictability and subseasonal timescales primarily, and that's the application here. So, so this is what the focus overall of the talk will be, is about the effect of climate change on predictability on subseasonal timescales. There's some assistance that I've received in this effort by a couple of colleagues from the Climate Prediction Center, Emily Riddle and David Unger has helped out a bit, and Tom Hamill has helped primarily with use of the data reforecast for the global Ensemble forecast system. So originally this abstract, as Bob pointed out, is a contributed abstract. It was not written with the work of Ed Epstein in mind. However, when I looked back a little bit at some of Epstein's work, realized that Ed worked on many topics central to climate prediction and related to the work that I have in this talk. So in particular, some of these things have been mentioned, of course, along the course of the day. He worked on detecting climate change in temperature records, early paper in 1982, which seems to me a very early paper in the efforts to detect climate change in the temperature record. Also, as has been pointed out much earlier in the day, from the very beginning, that Ed Epstein made one of the earliest descriptions of ensemble forecasting in 1969. I'm going to read that because it goes to some of the research that goes into this paper. So the initial conditions may be represented by an ensemble, as Ed says, each member of which is consistent with all of the available knowledge of the state of the atmosphere-ocean system. The mean of this ensemble is a reasonable best solution to the prognostic equation. He says, we have examined the behavior of the error in the forecast as represented by the deviation of the ensemble members from the mean. So in this statement, he's described an ensemble of forecasts, a mean, which is the best forecast, perhaps, in a deterministic sense, and then the error about that mean, which is a representation of the uncertainty of the forecast. So ensembles provide a foundation for model-based studies of predictability, which is what this analysis is a study of predictability. So using ensembles for predictability estimates. Ensembles are used to not only get the best solution, the most likely solution, but also to estimate the uncertainty, or conversely, we can say the predictability of the system. What do we mean by predictability? Well, the ensemble mean is an estimate of the predictable component of the future state. That is, there's chaos and noise in the climate system, so there's aspects of the future state that are completely unpredictable. But there's also some component of that future state which is represented by the initial state and can be derived somewhat through the ensemble mean. In this equation, the brackets denote the ensemble mean and the members by the x prime, and so some future state is a deviation from the mean plus the signal of the mean state. And so when you sum the variation of the individual members about that mean, or the different possible cases about the central mean, you get the noise component. So signal and noise, as represented by the ensemble, are dependent on that initial state. They're dependent on the particular time that the forecast is made and the associated state of the system. So predictability, or the degree to which the future state is determined from the initial state is dependent on that initial state. Shifts in the probability distribution indicate the strength of the signal. So these show ensemble forecasts and a shifting distribution from the climatology, which is shown in red. And the greater the shift, the greater the climate signal is in that case. And the wider the distribution, the greater the noise is for that particular forecast. And this is showing the spread is the representation of the uncertainty or noise. So a useful measure for predictability that's sometimes analyzed is the signal-to-noise ratio. So simply the strength of the variability of signals for a particular scenario, perhaps, or on average over a series of forecasts, and the variance about that central state, predicted central state, is the noise. The variance of the ensemble mean and of the individual members can then be used to give us a kind of correlation or a predicted correlation that whatever the ensemble system is predicting, it's an indication in the model world, what the correlation is expected to be. So here sigma of mu is the variation of the ensemble mean. The variance of the ensemble mean plus the variance of noise. If you take the ratio, if you add the noise to the signal, you get the variance of the observations. And so the ratio of the standard deviation of the variance in the ensemble mean to the total variability gives you the correlation as predicted by the model. So I just described that to you. Mu is the predictable portion. Epsilon is the standard deviation of noise. Sigma of mu is the standard deviation of the predictable part of the system. And so for a perfect model, we know that the variance of the mean is the predictable portion of the climate system. So often what we do in a predictability study is we essentially are assuming that the model is a representation of the actual climate system. So this gives us a potential correlation, a correlation if our model were perfect, as a function of signal to noise ratio. So along the bottom here is signal to noise ratio. Actually, it's inverted as noise to signal ratio. And going up, the y-axis is the correlation coefficient. For a single ensemble member, we get the blue curve here. And as you add ensemble members, you approach an idealized case, which is a perfect representation of the variance in the signal and the variance of noise. And so there's actually an upper limit to the predictability of the system, which even with a perfect model, you would get a correlation that's less than 1. So with climate change, we know that the mean state is changing over time. I'm going to use a simplified representation of climate change, which is a linear trend. So Bob Lizzie talked earlier about different ways to represent climate change. The period for which I have these reforecasts is from 1985 to 2010. So for that period, perhaps a linear representation is a fairly robust way of indicating climate change. So linear trends can be calculated for each of the components of the model system, and therefore a representation of the predictability in the system. So I'll calculate linear trends for the signal, for the noise. We can calculate it for the signal-to-noise ratio. We can calculate a trend of potential predictability represented by this idealized correlation, maximum correlation that's possible as indicated by the ensemble system. So if theta represents any of these parameters, and we have a mean for theta, then we have deviations or variance of this parameter theta, and then we can calculate the trend as a function of theta and time. So for any of these parameters, we can determine linear trends, and this is what I'll do in this analysis. So it's a reasonable assumption that since predictability is determined by the initial conditions, that predictability will also change if the climate state is changing. So particular characteristics of the climate system have an innate predictability, which one can estimate using a model. And if the background state is changing, then those initial conditions are changing, and the average predictability of the particular phenomena is also going to change over time, or would possibly change over time, doesn't have to. And so the question is, can we see that kind of change or variation in predictability in the model system? So why do we study predictability? Well, we study the performance of the forecast system, so how close is it to an idealized perfect model? We can use this kind of analysis to determine corrections to the output of the Ensemble forecast system. And we also want to understand and describe the innate internal uncertainty of the climate system. So as I stated, I'm using the Esrel reforecasts for the NCEP Global Ensemble Forecast System. This is an atmosphere-only model run out to the end of 2 weeks. 2 weeks is what was originally considered the end of the longest lead of predictable weather signals, but we're looking at this in an ensemble probabilistic fashion. So in that sense, we're looking at predictability in a probabilistic way, which could be extended beyond 2 weeks. There's 10 perturbation ensemble members plus the control, so 11 in all. I'm looking at week 2 averages. You could just as well look at daily averages. If there's a climate change signal, it would show up in daily temperatures as well. It just would be a smaller component of the variance. So looking at week 2, it's a larger component. And the initial conditions are from reanalysis, and this is what's used as an observation for this record. So in a 25-year record, we should be able to see climate change. So using a retrospective forecast system, or hindcasts, often what we assume is that the statistics that we use to make calibrations of the system are stationary. But this analysis is attempting to see if these statistics are stationary, because then we might want to adjust how we calibrate the system. So this is just a, from this forecast system, from week 2 forecast, this is just showing the distribution of forecasts over the entire United States. So the blue is just a histogram of forecasts for 1985, not sure if you can see that very well, 1985, 86, 87, et cetera, progressing through the years. It shows the full distribution of all of the forecasts for that year for the United States. The red curve represents the climatology of the week 2 temperature forecast as determined by the model. And what you see is that each individual year, the distribution doesn't exactly match climatology, but moreover, what you also see is that the distribution of forecasts seems to be changing over time, progressively moving from cooler climate state to warmer climate state as you progress into the 90s, with some internal variability, some variability from year to year, interannual variability, which would be due to variations on the interannual timescale, such as ENSO. So here you can see the early years, which tend to be cooler, and then there's clearly a multi-decadal signal and shifts towards later years, which tend to be on the warm side, and this is 2010. You can see that it's a year that is particularly warm relative to the climatology over the whole period. So in particular, this would impact the frequency of extremes. If the distribution is shifting over time, then the warm extremes would be increased in probability quite significantly. So let's move on to the results. I see I'm coming down to the end of the time. So this is the standardized linear temperature trend for the 25-year period from the forecasts. This is actually observed, so this is from the reanalysis. So you can see that standardized by the variance in weekly temperatures, that the trend is actually quite a significant component, and especially over certain areas, high latitudes. Not so much over much of the contiguous United States, but here in the southeast and southwest, it is actually a fairly significant component and over half a standard deviation in many areas. Shows up in the model forecasts as well, so they represent the trend fairly well, so that's a good thing. So the model does determine the trend fairly well. If you look at this in terms of the signal, which is the variation of the ensemble mean, you can see shifts in the variability of the ensemble mean as well. And this is different for winter and for summer. There's many areas where there's not much of an indication of shift in the signal, but there are areas across the tropics, for instance, and across parts of high latitudes where there's a very systematic change in the signal over time. If you look at the noise, however, there does seem to be perhaps a systematic change in the noise as represented by the ensemble spread. It's dropping over time in these higher latitudes in the northern hemisphere. However, overall, this is a smaller change than the signal. So if there's a change in the predictability, it seems like it's largely coming from the signal, or that is the variability of the predictable component of the system. So this is trends in the correlation. So this is a representation of predictability and how it's changing over time. You can see, for instance, here in the summer months, that large areas of the high latitudes of the northern summer hemisphere, that predictability is increasing as an indication that the signal, in part, is increasing. But these measures are in part, include the climate change signal. So it's not just a variability about a new climate state, but it's an indication that the model is capturing the climate change signal as well. So you would expect it to increase. So the previous slide was the potential predictability and its increase over time, or change over time, not always increasing. Change over time as represented by the ensemble. But if we just look at the actual correlation changes over time, this is on the same scale, which the maximum here is about 16%, plus or minus 16% in correlation. The actual changes in the correlation over the 25-year period are actually somewhat larger than those represented by the spread of the model. This is largely due to the fact that the actual correlations are somewhat lower than would be indicated by the spread of the model. So these are correlations around 40, 50%, sometimes lower than 40% here in the summer, sometimes higher than 50% in the winter in some regions. But you see here a shift representing what the trend would determine the shift would be in predictability over time. And you can see that there's a definite increase in predictability from the beginning of the 25-year period to the end of the 25-year period in practical sense, in the sense of what actual correlations would be. This is what the model is indicating the potential predictability would be, which is very high, 70, 80%, 90%. And now the shifts are much smaller, very, very limited shifts in predictability if you look at what the model indicates the potential predictability is. There's other important changes over time that need to be analyzed. This shows the bias, the trend in the bias over time, which shows that as the climate is warming, the bias is becoming increasingly negative. So that needs to be considered. So in conclusion, the trend is a significant fraction of interseasonal variability and part of the predictable signal. The systematic bias is changing over time. Regionally, it appears that the signal is non-stationary, and so it does change over time, and therefore the predictability itself also changes over time with climate change. That's it. Thank you.
Thank you, Dan. We don't have much time, but we'll try one question if you have it. Anybody with a question?
I don't believe it's changed. I believe it's constant. So part of the change in bias might be how the model reacts to initial conditions that are warmer or cooler.
Thank you. Okay, the last the last paper of the conference is given by David Unger. I gave you his bio earlier. He gave a paper in Virginia Beach in 1985, and it was on how to estimate the rank probability score, I believe. And Dave hadn't published on this subject before, and one of his colleagues said after it was over, "Where did this guy come from?" Because he just burst on the verification scene like that. So this is David Unger. He's going to give his talk on scoring systems for probabilistic forecasts for ranked climatology based on the RPS.
And at that conference, Al Murphy came over and said, "You're one of us now."
That was Don Gilman, by the way, that said that.
Oh, was it Gilman? Oh, okay.
Where did this guy come from?
Oh, that said, okay. Okay, we're going to be looking at the rank probability score. That's one of Ed Epstein's lasting contributions to the area of forecast verification. And uncertainty has always been an acknowledged factor in forecasting, but it's seldom quantified. To add insult to injury, some of the very first Weather Bureau forecasts from the newly formed Weather Bureau in 1871 weren't called forecasts at all. They were called probabilities, but there wasn't a probability to be found. And there was hardly any probabilities for nearly 100 years. Even in the mid-1960s, here you see an evaluation of the past couple of years of pop forecasts, and the probability of precipitation is still listed as experimental, even close to 100 years after that. In spite of that, I guess the meteorologists are cautious bunches because we had been looking carefully at probability forecasts for several decades. Here is Glenn Breyer's probability score reference, or the Breyer score, and that was published in 1950, 15 years before they were operationally available. Now, in the late 1960s, Ed Epstein was thinking, well, you know, weather comes in more than just yes, no, event, non-event. There are weather elements that have varying degrees of impact, and so Ed Epstein developed a score for use on evaluating probabilistic forecasts of ordinal forecasts elements, which I'll call continuous here. And this is his original note from the Journal of Applied Meteorology in 1969. We're going to be tracing the history of this score as it evolved through time. Here you see the number of references in AMS journal publications. I did a word search on ranked probability, and you can see that the number of references is plotted here, and you can see that it was over 30 years before the rank probability score began to appear in references. And if you want an explanation of that, I did a search on Ensemble members. That's a good proxy for the amount of published papers that are looking at ensemble forecasting methods, and you can see that in the 70s and 80s, the rank probability score references were mainly limited to theoretical or experimental forecast systems, and it wasn't until the Ensemble forecast systems hit the publications and became commonplace that the demand for evaluation methods, of good probabilistic evaluation methods, began to appear, and the rank probability score is among the leading scores in that arena. So we're going to look at how the original, Ed was clearly ahead of his time in developing this score. We're going to be looking at the original development of it, and it actually traces its origins to the economic value in a cost-loss decision-making framework. And we heard a little bit about this this morning. If you have looking at a two-category system, either the event occurs or it doesn't, and you either do something about it or you don't. And if the event occurs and you didn't do anything about it, you're subject to a preventable law. You have preventable weather-related losses, labeled as L, and in order to mitigate against that, you have some kind of an action that comes at a cost. If it doesn't come at a cost, you take that action all the time anyway. It turns out that if you should you should protect whenever the probability of the event forecast probability is greater than the cost-loss ratio. And Alan Murphy had been looking at the economic value of probabilistic forecasts, and from the standpoint of the forecaster. And the forecaster, of course, doesn't have any idea of who's using the forecast, or certainly not what their economic situations are. So if you're going to get a rough estimate of expected value, you can assume that there's a uniform distribution of cost-loss ratios among your potential users, and then you can compute an expected value by doing a integration across all users. And they found out, in fact, that the Breyer score is a appropriate evaluation measure for a two-category probabilistic cost-loss framework. Turns out that the value of the forecast is related to the climatological probability and linearly related to the expected Breyer score. So the Breyer score here is familiar to most everybody who deals with probabilities. Of course, the square difference between the probability of the stated probability of the event and the probability of the observation. Since it's an observation, it's either 0 or 1, depending on whether the event occurred. And so Ed said, well, most weather situations come in varying impacts. Let's look at get some idea of an economic value of a forecast in terms of a continuous element. And he did this by dividing, imagining an element in which he could divide the range of observations into a series of bins, such that there's a linear, such that the economic impacts are linear. So rather than just a cost or a loss, you have a cost or loss on either extreme, and no need for protection on the other. And in between, there's a linear increase in the cost of protection or a linear decrease, and a linear increase or decrease in the losses associated with the event. And since you don't know, for every farmer that's has to protect against a freeze, there's some commodity trader who's betting that the freeze will happen and will lose if it doesn't. So you have no idea of which side of the extreme your costs and losses are incurred. So you just integrate them overall and you calculate an expected value. And doing that, he came up with the original formulation of the ranked probability score, and this was formulated by the individual probabilities in each bin, and it came up with this rather hideous-looking equation that was close to his mathematical derivation, but not exactly the easiest thing to work with. Fortunately for us all, his colleague, who also worked at the University of Michigan at this time, realized that you could simplify that presentation by realizing that the RPS the original formulation was linearly related and was in the same family of verification scores as a Breyer score. It's a quadratic score with the working on cumulative distribution, cumulative probabilities of the forecast, cumulative observation probabilities, which of course are 0 or 1, depending on whether the observation is less than or equal to the categories that you're looking at. So this is the familiar rank probability score that Ed had come up with. We're going to look at, so here's an example, the Weather Prediction Center here at where I work at NCEP, makes probabilistic forecast of snowfall amount thanks to ensemble forecast, ensemble methods. And you'll notice that the scale is not linear here. The additional economic impact of an additional inch when the snowfall amount is around 1 inch is presumably much greater than the impact of an additional inch when a foot is already on the ground. So there's an attempt here that implicit in here is that the category widths have already been, are not regular, but they've been selected so that the impact on the society is perhaps about linear in that. And at least that's the way that RPS might treat it. And so you have categories here 1 inch apart, and then they go to 2 inches apart, and then 4 inches. And visualization, your forecast cumulative probability distribution among the bins are a discrete function here, and the OBS is in red, and that's a discontinuous function, either 0 or 1, depending on where the observation happened to occur. And the visualizing the RPS means that the forecaster really wants to minimize the error between the forecast distribution in blue and the observer's distribution in red. He or she wants to make that forecast distribution as closely matching the observation as possible. Of course, the area here, it's a squared area for the rank probability score. And one of the important concepts of any evaluation method, probabilistic or not, is a sense of a proper score. And that means that if the evaluation method needs to encourage the forecaster to state their true beliefs. And in fact, Ed Epstein had derived this score in such a way that it would. Perhaps Alan Murphy didn't fully trust him, so in a companion note to it, he proved that he proved that the RPS is in fact a strictly proper score. And so that means we can use it. And we can use one of the things that verification people who look at verification like to do is partition scores to look at various attributes. Here are some few important attributes that we'll look at in reference to the rank probability score. Fundamentally, the RPS is a measure of accuracy, which is the correspondence between the forecast and the observation. It's in the probability space. But you can also partition an RPS into reliability and resolution components. And here is a standard reliability diagram that many of us are familiar with forecast probability and the probability of event, and a series of bins of probability bins. If you stratify each, of the categories into bins of equal or near equal probabilities, and so you see that what a reliability score is a mathematical quantified measure of the area between the forecast to reliability and the ideal value of a slope of 1 here. And it's weighted by, of course, the number of cases in each bin, and the objective forecaster is he's rewarded if that area is small as possible. The resolution of this forecast comes in as a negative, so the forecaster wants as much resolution as possible, and that basically is a measure of this area. It says you want to have as much area as possible, so you want, when the event occurs, you can also calculate this from the reliability diagram. When the event occurs, you want to have low probability, and when the event does not occur, you want a very high probability, or the other way around. So that this maximizes, it tells you how well you're distinguishing, your forecasts are distinguishing events from non-events. And the uncertainty is out of the forecaster's control. It's related to the variance of the observations. Sharpness is really only meaningful in a probabilistic sense. It's a measure of the best possible score. And for the RPS, it's the sharpest, the best score is happens in the if your observation verifies in the category of the median. And finally, skill is a measure against a standard. The most common standard is a no-skill assumption that a climatological forecast is available to everybody, but also you can have persistence as a standard. Okay, so that's the rank probability score is defined in categories, but it wasn't long before people were applying limiting arguments to the category, shrinking the category widths to 0 and having more of them. And you have and this gives us the continuous rank probability score. You simply replace this summations by an integral over all the forecast domain. And it's the same thing, the forecast distribution and observed distribution as continuous variables. This was done in the early early to mid 1970s. Van Holsted was the first that I could see that coined the term ranked probability score. Visually, you can see if you're now dealing with continuous distributions, but the idea of this is the same. You have an observed distribution, which is discontinuous, but now that rather than restricted to category boundaries, observation can be anywhere, and the object of the forecaster is to minimize the area in the between the forecast and observed distributions. Okay, I like to look at it in terms of error diagrams, and here you see we're going to be looking at the forecast. Suppose that the forecaster places his median, and we subtract median and we look at the error, the score at various errors. And so at 0 error, if the forecaster says, okay, I'm absolutely certain the temperature is going to be this, the rank probability score becomes equal to the mean absolute error. This should not be surprising since Epstein derived it that way. He derived it with the idea that the value, the economic impacts are a linear function of your category, the number of categories that you're off. So that is what your score if you're completely certain. So if you lied and you weren't certain after all, and the observation, say, was -7, your CRPS would be equal to the mean absolute error, and you get 7 penalty points. Obviously, it's a negatively oriented score. The lower the RPS, the better the forecast. Now, I like to think of the forecaster specifying uncertainties is a little bit like buying insurance. So the measure if the median of the observation is observed, you get the lowest score, but the lowest score is no longer 0. You've bought insurance, and the forecaster is paid a cost up front for the privilege of expressing uncertainty, and the reward would happen in the case the forecaster has some bad forecasts. The probability score, he'll get a lower score, and that will diminish his losses. And so if he said, well, there's an 84% chance that the observation will be someplace between plus and minus 10, and the forecast error was -7, instead of 7 penalty points, now he only has 4 penalty points. Okay, so we're going to be looking at some other evaluation measures. There are not too many. The RLC is really is sometimes used in validation of ensembles, but that's really looking at a two-category system. I was unable to find a reference for a continuous multi-category ordered system. Telegram and rank diagrams or ranked histograms are often used for visualization, and we saw, in fact, that that's not a actual accuracy measure. It's just a single component of measuring a single attribute of forecast evaluation. It's actually a bias measure, and it's a partition of the this can be quantified as a partition of the RPS. And recently there's been some work on appearing in meteorological literature on the using a logarithmic penalty score. And basically that is the RPS is a quadratic, has a quadratic penalty. You can simply replace that with a logarithmic penalty, and many of the same attribute measures can be by analogy apply as much to the logarithmic scores as to the rank probability. Incidentally, the logarithmic scores go by the unfortunate name ignorance score. I really don't know why anybody would use such a name, but that's what they are sometimes, in fact, frequently referred to as. They look at the forecast in terms of information theory rather than decision theory that the RPS does. I just made a error diagram comparing the ranked probability score with a continuous ranked probability score with a continuous version of the ignorance score. I normalized them by their sharpness so that they each get the same error if they're exactly right. And the green is the CRPS, and the red curve here is the logarithmic score. And you can see here that if you think of it in terms of insurance, it's a cheap buy for the same cost of specifying uncertainty. You get a lot more benefit if you make small errors, but it pays out really lousy if you're making large errors. And put in perhaps a more scientific way, the ignorance score is looking much more carefully at the tails of the distribution, and by tails I mean looking at the slope only becomes greater than the CRPS when you're approaching 2 standard deviations above or below normal. Okay, so going back to our, so that's some of the competing scores. Now I'm going to go back into the original idea of the ranked probability score, going back to perhaps some of the more forgotten aspects of the derivation. And here you see that same 24-hour snowfall. Actually, this is a 48-hour snowfall. No, it's 24-hour accumulation, right. It was a lead time of 48. It was valid in late January, the same snow event that kind of crippled the local Atlanta area here. And here you see, in fact, this was the actual WPC probabilities expressed as cumulative probabilities. And notice again that the scale is not linear. And again, this is an acknowledgement that chances are, if you get 9 inches, if you predicted 9 inches, you'd be making about the same decisions than if you predicted 8. But there would be quite a bit of different decisions here if you predicted 2 versus 1. Now, to bring that to my object here is to make a continuous rank probability score that's equivalent to the RPS. And for that, some early references here. I like Matheson and Winkler's paper in 1976 introduced this idea of a generalized probability score, and you would call this a generalized CRPS, by adding a weighting function in with the penalty function. And the weighting function to choose is actually really easy. You just simply choose it to be the 1 over the bin width. And I like to, you'd also need to fill in the probability distributions, and I like a linear transition from one category to the next. It's equivalent to a linear increase in cumulative probability distribution. If you have an open-ended boundary, you simply weight that category as 1 over n, which is where n is the number of categories, and that's like putting a density spike so that you incur all of your penalty the instant that you go across that first or last boundary threshold. So here's our error diagram for Wilmington snowfall event. The actual observation was about 1 inch for the station. And what you see here is the errors are, you see a low resolution RPS focusing only on the exact bins as defined by WPC. But you can do a very good approximation of that by, again, using the weighting function. And you see the red line is the error function that you would get for varying snowfall amounts with a continuous version of the RPS. And so in conclusion, you'd use a straight-off CRPS. I think that's pretty much favored when the consequences of errors are linear relative to the element being measured. So, for example, economic consequences of errors in heating and cooling. We know that heating and cooling demand generally varies linearly with temperature, and so CRPS would be appropriate for that. You might use a generalized CRPS with a weighting function, and don't be afraid of that because the weighting functions are easy to figure out what they're supposed to be. When the critical thresholds are not linear, and that's frequently the case, not only in precip amount, but would be many, for instance, visibility or ceiling heights would certainly be nonlinear impacts, economic impacts with the varying element. And you can handle the unbounded first and last categories just as easily. And that should give you, if you're really interested just in the tails, you might consider using the ignorance score instead of the CRPS, because that's a lot more sensitive out there. So I guess the most important thing here is that you should understand that the original intent of the CRPS was to focus on decision support, and don't be afraid to, if you want more resolution than the discrete categories, don't be afraid to use a generalized CRPS to approximate the original Epstein ranked probability score. Thank you, David.
Okay, we finished on time. Any questions for Dave? Anybody used the CRPS? I'm sure many have. Yes.
The weighting function is applied, in the precept, it's a simple.
There you go.
The weighting function is quite simple to apply. It's just simply a constant within each bin, and it's equal to the bin width. And that reproduces the idea that each bin is the economic consequences are linearly related to your bins. Well, I personally never, I always use a continuous RPS, so I do. I think official verifications are still based on the RPS, But if you're doing experimental research and you're really trying to figure out differences between two forecast systems that are often quite similar, I think the additional resolution is very important.
Okay. Thank you very much, Dave, and I want to thank all the speakers that were in this entire symposium. I think it's been a good review of Ed's work. If you've been here most of the time and listened, I think you can really appreciate the depth and quality of this work and how much it has affected all of meteorology and so forth. Did you have a...
I want to give my heartfelt thanks to Bob and Dick Hallgren for putting this together. This was fantastic, and I'm speaking on behalf of the Probability and Statistics Committee, but I think I'm speaking on behalf of everybody here too. So thank you so much, Bob, and to Dick Hallgren as well. So thank you.
Okay, well that concludes the symposium.